So now we are having Hans Wenzl from all the way from UC San Diego. Hans, you probably don't remember, but you gave the talk after Vaughan Jones 30 years ago. I think it was on representations on rings of subfactors. So we're not very far today. Subfactors, tensor categories, and module categories. Thank you,
Okay,
Hans.
yeah, all right. Thank you for the invitation to this great conference. Of course, I would have preferred being in Istanbul, but okay, it's what it is. Yeah, okay, as already a bit too, I guess I'm still benefiting from Vaughan's insight. I'm still working on subfactors after all that time. So, and okay, so the plan is that I first review some very basic examples of subfactors, which probably already in some sense existed before Vaughan. And then I get to this kind of Q analog or Q deformations of these examples, which at that time was very exciting. And so there's basically two types of examples, which are called one of the tensor product subfactors, which will I explain, and the subgroup subfactors. So this tensor product type subfactors, this problem sort of, at least in this context of Q analogs of Lie groups, that has been solved like 20 years ago or more. But what's still unsolved are analogs of subgroups for these special types of categories. And so that's what I want to talk about. So I'll start very slowly with some basic definitions. There will be some overlap with Sorin's talk, but some of it will be a little bit differently presented because I think my focus is slightly different than Sorin's is. But okay, so let's get started. So of course, everyone knows Vaughan started this inclusions of factors, and his first important invariant, of course, is the Jones index, which is just giving you view the big factor as a Hilbert, bake it into a Hilbert space, and then calculate the dimension viewed as an n module. And the first really example, which is just if you have say you take R type to one factor, doesn't have to be hyperfinite, but so then you have a group G acting on it. So you look at the fixed points. Now, if you have a subgroup, then of course the fixed points are usually bigger. And so you get that the fixed points with a smaller group, both of them are factors because this is outer actions. And the index of this subfactors will be just the index of the subgroup. And that was why Vaughan called it an index, his invariant. Okay, now to get more interesting examples, one considers now what is used to be the Jones tower, at least Sorin referred to this as the Jones tower. But here I use a slightly different presentation, namely I take the relative tensor product of M with respect to the subfactor N. And of course I can do it more than once, so then I could take it N times. So I consider this tensor products. And now, of course, you can always act from the left and from the right with both N or with M. So you basically have four choices of viewing this as an X-Y bimodule, where X and Y both could be either N or M. So with this thing, we now obtain two tensor categories, namely the one of NN bimodules or of MN bimodules. And we can also obtain a module category, M, which is just MN bimodules, where you just are only allowed to act via M on the left and via N from the right. And this is in an obvious way a right C module category and a left D module category. So I mean, this is completely trivial. Here I just wrote down one of the things. Here, if you tensor, oh, what did I do now? What is it? Okay, good. Yeah, you see, obviously, man, if you tensor with a matching subscripts, then you get again another MN bimodule. Okay, now I deliberately don't want to go into this mess of giving formal definitions of tensor categories. It would take up maybe half of the talk, and so as far as this talk is concerned, you just to think of this as generalizations of the representation category of a group G. And essentially, the most complicated stuff can also always be realized as some NN bimodule categories. So you could just stay in the realm of von Neumann algebras. So it shouldn't be too scary or too abstract, too much abstract nonsense. Okay, now, so Rin already mentioned this in his talk now. So basically what he showed is that strong amenable subfactors, which again, I will not define. It's just all the examples we are dealing here with are strongly amenable. They are completely characterized by the category C and the module category M. Now, Soren stated this in terms, he used a slightly different formalism in terms of lambda lattices. And there's yet another description, which is due to Vaughan, which is via planar algebras. So these are all equivalent descriptions, and the approach I'm using here goes back to work by Ostrich, and which is, at least for my setting, seems to be the most convenient way how to deal with it. All right. So, as I said, Vaughan wanted to classify subfactors, so you have to find invariants. So again, let's go back here. So we have this tensor products of M tensor N, which decomposes into a direct sum of Mn.
Hey, Hans?
Do you hear Hans?
No, he went mute.
No,
Yeah.
I don't hear him.
Yeah.
Let me. Okay,
We got you now.
You have a,
Hans, we lost your voice a second.
Yeah.
Can you start again?
You're muted again, Hans.
you're muted again.
But he's not talking right now.
No, he was talking.
Yes, he is.
He is?
Can you hear me now?
Yeah,
Yeah.
now
Oh,
yes.
yes.
Oh,
Now,
okay,
yes.
good. Okay, thanks. Well, I hope it won't happen again.
Thank you.
All right, so we have a collection of so we do so it's basically the old approach of Hermann Weyl of studying representation theory. We just take tensor powers and look at all irreducibles within this tensor powers. So doing this, so for given one, we collect all the irreducible ones, which I call X lambda, which are all the irreducible NN bimodules. And I do the same thing by viewing this as MN bimodules. So like this. So then we define the principal graph as follows. So the even vertex, it's a bipartite graph. It's sort of what Sorin also referred to also in his setting as a standard invariant. So the even vertices are labeled by the irreducible and N bimodules. The odd vertices are labeled by irreducible MN bimodules. So now, if it takes such an MN bimodule, then of course I can restrict the left action from M to N. And so hence it decomposes into a direct sum of NN bimodules. And so hence the number of edges is given by the multiplicity of X lambda in Y mu, viewed as an NN bimodule. So it's basically just an induction restriction graph, which you have seen in representations with with respect to a group and a subgroup. So one cannot define a dual principal graph, but we won't bother with this here. So as an example, if you take the first example I already mentioned, the group and subgroup, then, and you play this game with the bimodules, you get back the induction restriction graph between the subgroup and a group. All right, so this is one class of examples. Another class is given by another type of outer actions of a group. So basically you take a finite dimensional Hilbert space and you take a representation, you consider this is as an G module, so it's a representation of G, finite dimensional representation of G. So then we get the standard how to find R, the hyperfinite to one vector as a closure of a UHF algebra, and we get the usual Xerox type product action of G on it, which I think is all well known. What? Okay, all right. Okay, so then we can find, can do the following. We have here the big factor, which is just the closure here of this one. And we basically just let the first factor be equal to the identity. So we don't have any matrices there. And we let G act on this. So we get a subfactor by just only allowing the scalar identities for the first factor. So I call this tensor product subfactors. And again, one can figure out quite precisely what this is. So the index is, not surprisingly, is just the dimension of V squared. And the principal graph can again be described via representations of G. So yeah, okay. I mean, it's probably not that important going over the details, but again, so the even vertices are given by the irreducible G modulus appearing in tensor powers of V tensor V bar, where V bar is the contravedian or dual representation. The odd ones are given by this guys here, where you take tensor powers of V tensor V bar and you tensor it again with another V. And again, the number of edges are given by some multiplicities in tensor products, which is yeah, fairly straightforward. As an important example, you could take for V the two-dimensional representation of G's SU2, which is self-dual. So hence then the index is 4. And one can describe the principal graph here by the infinite graph A infinity. And this graph comes from the well-known tensor product rules for SU2, which I think are also known. Okay, so, and I think these were basically examples known before Vaughan started his work. And I think at some point he mentioned to me that there were people around who, when he told me about his project, thought, well, that's probably all the examples you will get. So, and he didn't tell me who these people were, but anyway. So, of course, I mean, we all know now this was completely wrong. So let me restate again Vaughan's theorem, which Sorin already mentioned. So that the set of possible index values are given by a sort of a discrete series, 4 cos squared pi over L, which converges to 4, and a continuum of index values between 4 and infinity. What's also, for at least in my setting, interesting is that the examples he gave for this 4 cos squared pi over L were given by the finite graph AL minus 1. And so here the observation is, if you let L go to infinity, then obviously the graph AL minus 1 becomes the graph A infinity. And in fact, one can see in the limit, we actually do get back our SU2 example with the infinite graph here. So it turned out this is a special case of a much bigger phenomenon. Namely, you can essentially do this for any Lie group and for any representation. You can get a sequence of subfactors, which in the limit approximates the subfactor you would get here in this classical setting we had up here. And so this was done in like 98 by Fang Xu and by myself independently from each other. So, okay, well, maybe I don't know how, probably these technicals are not that important, but let me state quickly anyways. So if you have a semisimple Lie algebra, V a finite dimension G module, okay, D the ratio between the square lengths, that's not that important. It's either 1, 2, or 3. And we let Q to be the special root of unity. Then there exists a subfactor Mn with the index Q dimension of V squared. And the Q dimension can be calculated using Weil's dimension formula. Actually, this already appeared in Weil's proof of the dimension formula. This Q numbers already essentially appeared there. And so as example, for instance, for type SUN, oh, I guess I didn't say for which, okay, here I mean the vector representation of SUN, which I forgot to write here. You just get the Q number of n, which can be written here as sine n pi over L over sine pi over L. While if you take the vector representation of SON, then you get a slightly different Q number. So it's a little subtle here. So this all can be follows from quantum group theory, what these Q dimensions are. All right. So one gets a big class of examples of subfactors. Essentially, for every representation of a semisimple Lie algebra, you get an example. And maybe I should say here that these are not all examples, and probably in some sense, probably the most interesting examples have been what is called exotic subfactors, which are not connected to groups or quantum groups. So the first example was the famous Hoggerup subfactor, and a lot of work has been done since by like Morrison, Snyder, Grossman, Izumi, Liu, and others. So, but this is anyway. I have not worked on this, so but this is it was an exciting development, and so they reached a complete classification of subfactors up to index 5.25. So. Also, it seems by now it just goes beyond what one can reasonably expect for computer powers. Okay, quick thing about how was this construction of the subfactors done? It depended on two results. One was Anderson, which essentially he used this Drinfeld-Jimbo quantum groups. And the point here is for Q a root of unity. For this, the representation really becomes very complicated, but one can show that there exists a nice semi-simple tensor quotient of this representation theory with only finally many irreducible objects. So you could view this as sort of formally as you get from this representation category here with infinitely many points for SU2. And you kind of can cut it at a point depending on the root of unity, and then you get back a finite graph. This is for SU2, and it's more complicated for other Lie groups. All right, and so essentially a big part was already done by Anderson, and then the only thing which was left to do, which actually turned out to be less trivial than it might appear, is that this category as FGL didn't have any C star structure. And one can then show with some effort that one can supply this with a C star structure and can make it into a C star tensor category. A C star tensor category just means that the homomorphisms are Hilbert spaces and that the endomorphisms of an object representation are C-star algebras. So, and finally, also that the star operation is compatible with the tensor product operation. Okay. So having the C-star tensor category, then you can play the same game as before with construction of subfactors. So basically, what you do the same thing what we did above here. Where was it here? The only thing is that instead of having the group representation, you do the same operations in this C-star tensor category. Okay, so we are now, this was back in 98. And in some sense, at this point, I thought, okay, this, at least for this type of subfactors, we are done. There isn't really much to do. Of course, what I didn't think of at that time is that what about trying to get analogs of the subgroup type subfactors? So sorry, I'm still not, sorry for my low-tech approach here, but I'm still not that high-tech with this, this talk presentations. So yeah, so what do I mean by this subgroup? Let me first say, so we would like to extend the notion of a subgroup to the setting of these tensor categories. So how can we do this? Here is a kind of a trivial observation. Let H and G be groups. Then rep G is a module category of rep G with the module action given by restriction. So this is kind of a triviality. So if you take W, a representation in H, and V, a representation of G, then your module action is given. So here on the left-hand side, the tensor product sign stands for the module action. And this is just defined where we make V into an H module and then take the normal tensor product of H module. So this is kind of a complete triviality. So the notion of the analog of a subgroup in this category setting would be a module category. So hence we get now the question, what are the module categories of FG, of such a fusion category, which we found up here by some complicated quotient construction. And maybe this is not just some completely esoteric thing. This question is also of importance in mathematical physics for finding models for boundary conformal field theory. Whatever this is, I will not go into this. But a lot of work has been done by mathematical physicists on that subject. All right, so known results. Of course, Vaughan already made some contribution to this right away way back in, I don't know when, probably in the 80s already, and with the Goodman-de la Harpe-Jones subfactors. So we did it for the C, the category of NN bimodals for the Jones subfactor. So then one has a very nice classification of the module categories. Namely, the module category, there exists a module category. This is for each graph of norm 2L. Yeah, I'm sorry, but really not. Yeah, okay, I hope you can read this. Okay, so again, if you look at the category of a Jones subfactor of index 4 cos squared pi over L, then you get a module category for each graph of type AN, DN, or E6, E7, E8. Of course, here the graph depends. So we have at most 3 different module categories for a given L. So it could be all right. So this was for the special case of the Jones subfactors. Now, a complete classification was achieved for these fusion categories for SL2L and SL3L by work of a lot of people like Ognano, Jones, Izumi Kawagashi, Gannon, Evans, and probably also a few more people. And this is already quite complicated. So for the SL2 case, it's basically an ADE classification. And for the SL3 case, it's somewhat more complicated. And so this classification was used by many clever ad hoc methods and computer power. And there are now more results have been achieved only recently by Gannon, Chopire, Eddie Mitchell for an important subclass of module categories called quantum subgroups, but which have somewhat nicer properties and also somewhat more important, but I don't want to go into this. All right. So now the idea is, okay, can we find some of the more conceptual construction for of such module categories? Because often it's not even clear what can we obtain. And so one is a very naive idea is, what about if you take a Lie subalgebra of H of G? So we have seen subgroups give module categories. So can we pull this embedding H in G up to the level of fusion categories? And so the answer is, which we're going to describe, yes, for the embedding of two cases, namely, if you embed the orthogonal groups into the special linear group, and for the symplectic ones into SLN. So again, for the special case n equals 2, which is basically SO2, or one should think of O2 embedded into SU2. These are already constructed by Goodman-de la Harpe-Jones, and you get the special case of the Goodman-de la Harpe subfactor for corresponding the graph Dn. And one can calculate the index, which is given by this number. So let's do the next case here, with n equals 3. So then again, so there's some complicated formulas now, which is probably not that important to know what this is. So one can calculate this, one obtains subfactors with this given by this complicated number. And one can also describe the principal graph of this. And in some sense, you'd think of this, again, I guess I gave you some lengthy description of this, but it's really not, in principle, it's not, the idea is not that complicated. So basically, one has both a finite subset of irreducible representation of SLR, which will label the even vertices, and we have a finite subset of irreducible representations of SO3, and the edge will just be given by, again, some restriction rule. So probably the most intuitive thing might be this statement here. Essentially, you obtain the principal graph by essentially truncating the induction restriction graph for a representation of SO3 into SU3. So these subfactors, you can view this as finite approximations of the cosine space of SO3 into SU3. Now, there are a lot of subtleties in this, which only some of it already became apparent while working on this. For instance, this construction only works for L odd. So if you have an odd root of unity. If you want to try the same construction for an even root of unity, positivity will fail and it just doesn't work. Now, however, there has been independent work already earlier by some completely different methods using loop groups by Feng-Zhi and earlier late with Victor Katz and Roberto Longo. And so they could calculate it also the indices of subfactors for SU3. And there it says for L even, you need to find a different embedding, namely SL2 into SL3 in the normal way. So again, this is maybe a conceptually more interesting thing, but it's very hard to calculate anything with that approach. And so Xu's method only applied, he could only do it for n equals 3. So the advantage here of the method which I used is that you can actually do calculations in the general. And again, I don't think one needs to go through all this detail, what I wrote down here in detail. So the idea is, again, fairly simple. So you view SLN as an SON module. I think let's just stick with SON. We don't need to do SPN. So then it is known, if you view SLN as an SON module, it decomposes into the direct sum of two irreducible representations, SON itself and a complement, which will again be irreducible. So then basically what you do, you view this P as an SON module, and using information which from representation of Lie theory, you can use this to calculate the index. And I mean, I think, again, you get some complicated formula, but everything can be calculated explicitly. And if someone is really interested, then I can talk later about that, or talk about the details of this paper. So, and again, here one can calculate the, sorry, okay. Maybe one thing is, what I just want to say here in the corollary is that the index, if Q approximates 1, then the index will go to infinity, as it should be, because in the classical case, these are both infinite groups, SUN and SON, and with the index infinity. And it approximates infinity with asymptotics, the dimension of P. So like in our case, if you want to check it for SL3, you can check here that this will be asymptotics will be 5, L to the 5th in this example here. And again, as I said already before, you can do this. You can calculate the principal graph, which is again some truncated induction restriction graph between the classical groups. Very briefly about the construction. So this is what the method was based on some very in principle elementary calculations. What we do, we know in the classical case, we could construct this subfactor from this embeddings here, which I wrote down here in this line. And the SON is a subgroup, so hence the centralizer is bigger. So one gets a sequence of finite dimensional algebras. With n goes to infinity, one gets the subfactor. And one even knows this is essentially, one can describe explicitly by the Weyl theorem, Schur-Weyl theorem. The endomorphisms are given by the symmetric group, and the endomorphisms here are given by something called the Brouwer algebra, which is known. Then the first thing is that the deformation of CSN, it has to be a well-known algebra called the Hecke algebra of type AN-1, which has been well studied. Now this, together with compatibility conditions, which for people who know it is called the commuting square condition essentially, and for conditional expectations, forced relations of the Q deformation of the Brauer algebras. So, and then it basically boils down to linear algebra, combinatorics algebra. So, all right, this is a rather tedious construction. So it would be nice to have more conceptual constructions. So, you know, this method, which I think has the potential to work in other specific cases. So maybe for the case SL2 and SL3, which I already mentioned before, it should be possible to do this. But it seems a rather messy method to do in general. Now, I think I probably could have done this case, which I did a long time ago, but I really tried to avoid this and was looking for something more conceptual. Something which looked promising was the following. There's the concept of a co-ideal algebra. So if H is a Hopf algebra, a left co-ideal algebra is just a subalgebra satisfying the fact that the coproduct ends up in B tensor H. So it is not a sub-Hopf algebra because they are very hard to find and very hard to construct, but it's a co-ideal algebra. So only, say here in this case, the left part has to be in B and the right part has to be can be in H. So it's very easy to see that rep B is a model category of rep H, which follows from the definitions. So we already have a model category, except of course the problem is that we are interested in whether we can pull this over to these fusion categories. So, okay, sorry, I went ahead. So a large class of such co-ideal algebras were constructed for quantum groups. So we have lots of co-ideal subalgebras for these quantum groups. And they essentially correspond to symmetric spaces. However, as I said already before, I have not seen any way how to pull this over to the fusion category setting, or how to find a C-star structure on this representation category. So, and so I may not have worked hard enough on this because I looked at this off and on. So, but by now I almost tend to believe that maybe this does not work. So I think the other method would just be going back to this Katz-Longo-Jus work using loop groups. Even so the explicit calculation of indices seems to be very hard, there's still a lot of specific data in this setting. And so I would hope that maybe this, using this data, perhaps together with this categorical approach, which I used before for this other setting, might at least construct more examples so that maybe one gets a clearer picture what's possible or what is not. So I think I have to leave it with that. So at least there are some partial results are known, but I think it would be really nice to know how many model categories one could find by just looking at the classical representation theory and some deformation. Okay, I guess I was a little faster than the allotted time, but
no, it's
getting late, so I don't think people will mind if they have to get a little earlier off.
2 minutes less, not much.
Yeah.
Thank you very much, Hans. Do we have questions?
Maybe in the remaining minutes, could you explain your Q deformations in a little more detail?
Oh, okay. So, well, okay. Let me now see. Let me see whether I can back, because I have a blackboard behind me. So let me just see whether I can. Then I get.
You can stop sharing.
Yeah. All right. So, all right. So then, okay. So. So the Q deformation is the following. Can you speak? So here we look at CS. Let me turn on maybe the light, then that makes it. So we have here, the classical situation is we have CSN into the Brouwer algebra Dn. Now the Brouwer algebra is essentially has one additional generator. So so basically, if you describe permutations like graphs like this, so pi of I, then the Brouwer algebra also allows some horizontal guys like this, which come from contractions in tensor products. So, all right. So then, now we know that if you go to the Q deformation here, then we get something called the Hecke algebra, H and Q, where essentially now we have to worry whether it's an overcrossing or an undercrossing, but that's good. So now essentially, of course, this has to be a subalgebra of this Q version, D and Q. So where we have, so we basically we just need to now figure out what are, how does such a vertical guy interact with these crossings here. And for doing this, that we know that to get a subfactor, we need to have what's called the commuting square condition. So that means essentially, if you have here CSN, or let's say HN, which we can bed into HN plus 1, then here we have DN, and maybe Q, and this is in DN plus 1 Q, embedding like this. So then we need to have traces on this such that the conditional expectations on this and on this commute. That's called the commuting square condition. Think of it, so we want to have these star algebras with this kind of embedding. We have traces on this, so we have conditional expectations, and then the condition is that the conditional expectations on this have to commute. And for this to be satisfied, forces basically the algebraic relations for this algebra. So that's essentially, and I think in principle it could, and now here, these algebras are comparatively well known and have comparatively simple relations, so it could be done. But doing general like for anyway, but I don't want to go over the time. So
thank you very much. Thank you very much.
Well, this was perfect timing. We still have time for some questions, if there are more. It was nice to see a board, a real.
Yes, I must say, when I had office hours students, I finally could explain something on the blackboard. It really felt like back to good old times, and so I like this if I can use the blackboard.
Yeah. That's how I've been teaching, actually. This is how.
Yes, I felt like maybe I should have done it too, just doing it on the blackboard. It's yeah. Well, anyway, I hope we can get back to normal. At least our chancellor told us that he really wants to get back to normal in the fall. So, and it seems right now in the US, there seems to be a good chance we may be able to do it, which would be nice.
Well, let's thank Hans.
All right, thank you.
Thank you.
Thank you very much, Hans, for participating.
Well, thank you for the invitation.
We have one last